So the basic concept of Archimedes' principle is simply that when you place something all the way in a fluid, you displace the fluid, and it makes the level of the fluid rise. So, Archimedes, was able to show how much gold there was in the king's crown by submerging it in water. And I don't know if the story is real or just hyperbole, but it gets us a start, and many of you have heard the story before. What we're really going to talk about today isn't so much that, but a related thing that Archimedes didn't know about, kind of, but something called the buoyant force. And the buoyant force is a force that exists on objects that are within a fluid. So you're all experiencing a buoyant force because you displace a fluid. You displace air, and therefore there's a buoyant force on you. A buoyant force does exactly what it sounds like in the name. You live in Florida, so you know what buoys are, or you should. If you don't, who doesn't know what a buoy is?
I don't know.
Oh, that's good.
It's like a floaty?
It's kind of like a floaty. Usually a buoy is anchored to the floor of whatever the water body is to mark something. So a buoy could be used to mark maybe the side of maybe an obstacle in the water. So maybe there's a rock or something there that's big enough where it could injure a boat or injure you if you jumped in the water. We use markers to mark the way in and out of channels so that boats know it's safe to go on a plane there without running aground. So we have markers that are actually physically implanted in the ground. We also have marker buoys, especially in areas that might change. So Hurricane Pass between Caladesi Island and Honeymoon Islands, and many of you probably been to Honeymoon Island before. No, never?
I don't know. Yeah.
Honeymoon Island is in the Dunedin. So if you go to Dunedin Causeway, the beach that's there, that's Honeymoon Island. You should go. It's considered one of the number 1 or 2 beaches in Florida.
I thought it was like Clearwater or St. Kitts.
So you drive 40, 50 minutes to go to a place when there's a nicer beach 20 minutes away. It is true, though. A lot of the kids like to go to St. Pete and Clearwater because that's where all the other kids hang out. But let me tell you, you're missing out. Honeymoon Island's beautiful. Oh, you go where you go. So, anyways, marker buoys obey this principle. They have a chain that usually is hooked to something that's in the ground, but they are buoyed to the surface, meaning they experience a force that is towards the boundary of the surface or the level of the surface. So a buoyant force. There's one that acts on you guys. Now, a buoyant force doesn't necessarily mean something's going to float, by the way. The conditions for floating are different. We'll talk about that. But anything that's surrounded by a fluid is experiencing a buoyant force. Now, that buoyant force is particular. The buoyant force is equal to the weight of the fluid displaced. I'm not going to say that a billion times, but that's actually the important point, that the buoyant force is equal to the weight of the fluid displaced. Now, Archimedes didn't fully appreciate the idea of forces because that would come later with Newton. So, although he understood the idea of displacement and he knew that things would be pushed to the surface, they had different ideas about what was happening. Now, if you remember something we talked about yesterday, I said to you that when you are under or inside a fluid, you are experiencing pressure. And I think we talked about the difference between actual pressure and gauge pressure. I'm not sure we made it that far or not. But one of the principal things here is that pressure depends on how deep you are. So if you have an object inside a fluid, the deeper you are, the bigger the pressure is. Well, we know that pressure is also a force, right? Pressure equals force over area. We talked about that yesterday too. So if we didn't, then we probably should. Did we talk about that yesterday? Yes, we talked about it yesterday. So the sides of this box are experiencing the same force because they're at the same depth. But the bottom of the box experiences a bigger force than the top of the box does. Again, the box is experiencing pressure all around because it's inside a fluid. But because the bottom of the box is deeper than the top of the box, the difference in pressure causes the buoyant force. So the buoyant force is a result of experiencing different pressures at different depths. Luckily, we don't have to worry about calculating the pressure to calculate the buoyant force. the buoyant force, because it's based on the fact that it's the difference in pressures, doesn't really matter where you are in the fluid, because the difference in pressure stays the same no matter how deep you are, because it's based on your size and how much deeper one part of you is than the other. So the buoyant force is equal to the weight of the fluid displaced. Now it's a weight then, and we know how to calculate weight. Weight is mass times gravity. So the buoyant force would start by being equal to the mass of fluid displaced times g, right? Because that's the weight of the fluid. The problem is that how do you know how much mass of fluid is displaced? Especially when I indicated just a minute ago that it really has to do with the shape of the object. So what we'd like to do is convert the mass of the fluid to something that has to do with the shape of the fluid, and that's actually really easy because you guys know things about chemistry. You know that the density of an object is equal to the mass divided by the volume. Right? So here's the thing. I want to put this in terms of the volume of the object, but we're talking about the mass of the fluid. So if we solve this for mass, we'd get density times volume. But this would be the density of the fluid, while this would be the volume of the object. So I'm going to use an F here to indicate that that's the fluid, and an O here to indicate the submerged object. Is that okay with you guys? To try and differentiate? And this is the mass of the fluid. So we take the volume of the object, put it in the fluid, and the amount of fluid that's being displaced is based on the shape of the object, because it's the thing displacing the fluid. Is that good so far? All right, we're just going to put these two things together, and we'll get that the buoyant force is equal to the density of the fluid times the volume of the object times g. That is the weight of the fluid displaced. Yep.
How do they do this on like large scales, like with bodies of water? Or do they like position things?
I don't understand the question.
Like through, like.
Which is something we do need to talk about, is that this buoyant force does not tell you whether you float or sink. This is just how much force you experience displacing the fluid. Now, a diver diving in salt water is probably going to experience a bigger buoyant force than a diver in fresh water, because salt water has a higher density than fresh water. So because the density of the fluid is greater, they experience a bigger buoyant force. They also experience more pressure at the same depth that they would if they were in fresh water. So does that make sense, that answering parts of your question? Now, we're going to play around with this on Tuesday. In fact, we're going to make something called a Cartesian diver. And some of you have probably made this, but I found that most people haven't. If you want to play and do this activity, you'll need to bring a clear plastic bottle with you on Tuesday. I'm going to make one in front of you on Monday, and then you guys will make one Tuesday. It can be done with like a water bottle, but if you want to enjoy the activity more, a 2-liter bottle is more fun, but then you have to deal with having a 2-liter bottle. So you need the top. If you don't bring the top, it won't work. Everybody understands? But we'll make them on Tuesday. You won't get to keep them, because I'm going to be using something that I need back from you. It's just a glass, a small glass test tube, but I'll need to get it back because I don't have enough for you to keep. But just bring them on Tuesday. It'll be a fun little activity. It won't take the whole class, but it'll be fun. Now, I do need to bring something else up here. This does not talk about whether something sinks or floats. This just tells you the upward force on the object in the fluid. The object is still experiencing a downward force, and that's gravity. That's the mass of the object times g. Sinking and floating is about these two forces. So I'm going to say this out loud. even though it sounds ridiculous, but if the buoyant force is greater than the weight of the object, then it floats. And if the weight of the object is greater than the buoyant force, then it sinks. It's that simple. So when we talk about whether something sinks or floats, it's about back to F equals ma, and the buoyant force is upwards and the weight is downwards, and that tells you whether you sink or float. If it's 0, you're at neutral buoyancy, which means you don't sink or float. So a diver tries to usually attain neutral buoyancy. So they're not constantly changing up or down. Fish do the same thing. Fish have what's called a swim bladder, and a swim bladder has oils in it. And the fish attempts to maintain neutral buoyancy because otherwise the fish would be more dense than the water and it would just sink to the ground. And it would have to use energy to not be on the ground. Now there are some animals that don't have swim bladders, and they have to expend more energy just to be able to stay at certain depths. Otherwise they sink to the bottom. Submarines do the same thing with what's called ballast tanks. They carry tanks of air that they can change the volume to basically maintain neutral buoyancy. Now, it is appropriate that we consider whether something sinks or floats and what the conditions would be for that. Right? If the left side is greater than the right side, we float. If the right side is greater than the left side, we sink. If they're equal, we have neutral buoyancy. So if we want to compare what it would take for something to sink or float, we would have to compare these two forces. Now, it's hard to compare this because this is the mass of the object, but this is the volume of the object, right? So I want to do a little bit of math here to make this comparison, okay? First, we can get rid of g in this comparison. It's the same on both sides, right? I'm going to divide both sides by the volume of the object. Now, do you notice something? The mass of the object divided by the volume of the object has got to be the density of the object. So I know this is obvious, but some of you probably learned this earlier in life, that things that are more dense than the fluid sink and things that are less dense than the fluid float. This proves it. So if the density of the fluid is greater than the density of the object floats. If the density of the object is greater than the density of the fluid, the object sinks. It's that simple. And if they're the same density, well, then they have neutral buoyancy. So we're going to play around with that a little bit on Tuesday, but I'll make the Cartesian diver for you to see on Monday.